everyone, and welcome to today's Explainer. We are diving into the journey of the spark, from chemistry to combustion. Every single day, millions of times a day, there is this incredibly violent, high-voltage process happening completely hidden right beneath the hoods of our cars. Today, we're going to track that incredible journey. We'll see exactly how a quiet little box of chemicals transforms into the roaring combustion that literally hurtles heavy metal down the highway. So you might be wondering, how does a simple box of acid actually start a massive metal engine? I mean, think about it. On a freezing cold winter morning, how on earth does a small box of acid and metal manage to crank over a massive heavy iron engine? It's kind of a physical paradox, right? Well, the answer requires a dramatic, instantaneous transformation of energy. Let's break it down visually. The whole journey starts right here, with something you've probably seen 100 times under the hood. The classic 12-volt lead-acid battery. This familiar black box is an electrochemical device, and it acts as the primary source of electrical energy for nearly all vehicles on the road today. Whether it comes wet charged straight from the factory or dry charged and waiting for activation, this box is absolute ground zero for our spark. Now, I have to bust a quick myth here. We all casually say a battery is out of juice, right? But it's absolutely crucial to remember that a battery doesn't actually store electricity. It's not a bucket just holding electrical charge. It stores chemicals. It houses this highly precise sequence of reactive materials that convert chemical potential directly into electrical energy exactly on demand. If we zoom in and look inside the battery, which typically has 6 separate cells for a standard car battery, we see a beautifully precise arrangement. Picture this. You've got these brown-colored lead dioxide plates that carry a positive charge, sitting right next to gray-colored sponge lead plates holding a negative charge. When they're bathed in a very specific liquid mixture, these contrasting metals react and generate that electrical pressure we call voltage. Speaking of that liquid bath, the electrolyte, it requires absolute chemical precision. To put it into perspective, in a fully charged state, that solution is exactly 36% sulfuric acid and 64% water. No more, no less. This highly engineered acidic environment does two things. It fuels the chemical reaction itself, and it conducts the resulting electrical current from plate to plate. But here's the really cool part. Unlike standard flashlight batteries, those primary cells that just die forever once their metals are depleted, the automotive lead-acid battery is a secondary cell. That means it's a reversible cycle. As it drains, the acid weakens, but if you route current back into it using the car's alternator, the whole process literally runs in reverse. It restores the plates, strengthens the acid, and boom, it's ready to spark all over again. So this endlessly cycling powerhouse is constantly juggling 3 distinct jobs. First, when the engine is off, it's quietly powering your lights and accessories. Second, and this is by far its most demanding job, is engine starting. It has to instantly deliver a massive surge of energy to the heavy starter motor while simultaneously feeding the ignition system. And third, once the engine is actually running, it acts as a backup, supplementing the charging system whenever there's a heavy electrical load. Okay, so how does that 12 volts of chemical energy actually ignite highly pressurized fuel? Well, it first enters what we call the primary circuit. This is the low voltage pathway. It pulls those 12 volts directly from the battery, routes the current through your ignition switch, and stages it right inside the primary winding of the ignition coil. Think of this as the crucial setup phase of our journey. But here's the catch. 12 volts is absolutely not enough pressure to jump the tiny gap of a spark plug inside a highly pressurized engine cylinder. Not even close. Enter the secondary circuit. This high-voltage pathway is where the heavy lifting happens. The entire purpose of the ignition system is to safely and instantly transition energy from that primary circuit over to the secondary circuit, multiplying its power exponentially. If you look at the blueprint of this power transfer, you can clearly see how they work together. The low-voltage primary circuit feeds the system from the top, while the secondary circuit waits below, ready to deliver that massive high-voltage spark. And the bridge connecting these two totally distinct electrical worlds, that is the ignition coil. It's the literal transformer of our story. Now, you might be asking, what's the secret to multiplying that voltage so dramatically? It all comes down to the physical wrapping of the wires inside the coil. Around a shared, highly magnetic iron core, the primary coil uses a mere 100 to 200 turns of wire. But the secondary coil? It's wrapped with 15,000 to 25,000 turns of incredibly fine wire. That massive disparity in wire loops is exactly how a simple 12 volts scales up to tens of thousands of volts. And here is where the true magic happens. Those two coils, they never actually touch. It is pure magnetic induction. The 12-volt current from the battery magnetizes that iron core, but the second a trigger signal tells the control module to cut that primary current, the magnetic field violently collapses. And as that collapsing field sweeps across those 25,000 turns of secondary wire, it induces a massive, instantaneous high-voltage surge. The spark is born. Of course, modern engineering takes this whole process even further with the distributorless ignition system, or DIS. The old mechanical middleman is totally gone. Today, individual cylinders often get their very own dedicated ignition coil. This setup is tied intimately into the vehicle's computer, dictating the firing order with absolute digital precision and perfectly timing that magnetic collapse for peak engine performance. All of that complex chemistry, the precise digital timing, the incredible magnetic induction, it all boils down to a microscopic window of time, 1.5. In modern systems, the average firing time across a spark plug is just 1.5 milliseconds. To cleanly burn today's leaner, more emission-friendly air-fuel mixtures, that tiny fraction of a millisecond is literally the difference between a smooth, powerful ride and a rough cylinder misfire. It really is staggering when you take a step back and look at the whole picture. I mean, in the literal blink of an eye, acid reacts with lead, generates 12 volts, magnetizes a core, collapses a magnetic field across 25,000 wires, and blasts a high-voltage lightning bolt for exactly 1.5 milliseconds. If all of this unseen brilliance is happening flawlessly thousands of times a minute, what other hidden engineering miracles are happening right beneath your feet every single time you drive? Thanks so much for joining me on this explainer, and keep wondering about the incredible world around you.